Good afternoon, everyone. I'm Hirak, and excuse me for my weird voice. Excuse me for my weird voice for last 2 days. Um, uh, so I'm working on level 3 biosensing, and mainly we are working towards in situ biopsy. And while discussing, and I'm mainly working on apta-sensors. So what is apta-sensor is like I was discussing with many of the scientists, and then many of them are surprised. Like, what is what is an apta-sensor? Apta-sensor is basically where it's a kind of biosensor where the recognition molecule is aptamer. And aptamers are very small short stretch nucleotide, and it has unique kind of secondary and tertiary structures. And it has a very different way of recognizing your molecules. So how do they usually work is like you have an initial library of small stretch aptamers, and then you put your target in, and then some of this secondary structure will bind to it. And when they will bind, you just watch the rest of the aptamers or nucleotides, and then you dilute only those who have bounded to that. And then you can just amplify them and put some stringent condition, and then again do the cycle again and again. So if you do this cycle again and again, at one point you'll be finding that your aptamer is very, very specific to your particular target. Hello, is it fine now? Okay. Yeah, sorry for the inconvenience. So at one point you'll be finding that your aptamer is very, very specific to your particular target, and that's how it works. And this particular system is called SELECT, systemic evolution of ligand by exponential enrichment. And now, coming back to the fact of why we need in situ biopsies, like these are some facts that already, like, if our therapy and the diagnosis system continues like this as of today now, so we'll have at least 30 million deaths by 2030, and in an increasing rate. So it might increase. And the secondly, metastasis, even in the last report, last month, even who reported that metastasis is the most cause of death out of cancer. And they have also mentioned that 95% cases can be saved if we can diagnose them at their very early stage. So now early detection is the first line of, you can say, defense, where you can save many of these lives. But it is very, very difficult to detect at their very early stage. As of now, there is not a single biomarker exist in this world which can confirmly tell that okay, you might have a cancer down the line, maybe 1 year later or 2 year later or something. On top of that, like if you have a kind of benign cancer or tumor cells, that is not at all a problem because that is localized. You can excise it, you can remove it, you can have chemotherapy. But the problem is when they started spreading, you will have a very, very less control on them. And now, in most of the cases, it has been found that when a patient has been died, in 70 to 80% cases, they have died out of like lung disorder dysfunction or liver or some other organ failure. It's not about due to that particular cancerous cells. So it is very, very important to detect those in their early stage. So now the concept is coming, like whether we can detect the early stage cancer cells, whether we can detect some cancer cells at their very, very early stage. And so the SELECT method, it has, as I have shown you during the aptamer selection, it has some sort of unique characteristics. I'll tell you just later. So what happens at the beginning, like you have normal organ with normal cells, and that has been transformed to the cancerous cells. There is no problem with that. If you have only localized cancer cells, you have thousands of treatments available, you can have it. But the problem is, like what they try to do at their very early onset, they try to leave some cells, like 1, 2, 3, up to 10 cells per ml, and they try to find a new home. And that is the onset of the metastasis. And this is a kind of characteristics of their own. So they try to find a new home to spread the whole thing. So if you have like these normal cells, like skin cells or whatever, the cells are epithelial in nature, and that cannot be like traveling inside the blood. Other immunological systems will come and kill. What they used to do, they used to have a kind of process which is called EMT, epithelial mesenchymal transformation. And then they have a kind of characteristics which is nearly to the blood cells, and they travel along. And when they find a home, they do the reverse thing, MET, mesenchymal epithelial transformation. And then they try to find, anchor them, and try to have the micrometastasis, which has been converted to the metastasis. The problem is, like you have to capture these cells within this travel period. And what is the time period? It's like less than 3 hours. Now tell me, I mean, which kind of sensors can really screen your blood within 3 hours and try to find those among like 10 to the 1 9 cells per ml? So the idea is coming whether like whether we can directly sense those whole cells rather than sensing a particular marker, because within 3 hours you will have at least several thousand molecules have been changed on the cell surface due to EMT, and that has been reversed back when this MET happened. So this epithelial mesenchymal transformation actually changes thousands of molecules on the surface. So if you have any target molecules or the sensing element, that has been changing within these 3 hours alone. So if you have a particular target or something, that will be missing for sure. And there are many ways of like physical and chemical ways of isolating this one. But the problem is you have only 5 liters of blood, and it's not possible to centrifuge your blood to do something and to extract those 10 and 15 cells. And that is at the very early stage of the thing. So the Select method is now available for whole cell sensing. How does it happen? That if you'd like to identify those cells in the bloodstream, so what they used to do, you have the random again aptamer gene pool, and then you are putting your blood cells where you want to detect for negative selection. So those who are bind to the blood cells, you will be, you will be taking the unbound variation because this is specific to the blood cells. And then after one round of this, you put your target cells here and then do the positive selection. So first you are eliminating the possibilities that your aptamer will not specifically bind to your blood cells, and then you are putting your target cells and trying to do the positive selections. So in this way, you can have a very specific aptamer which can recognize the whole cells. And now if you ask me, like, a cell is a cell which has thousands of receptors and surface molecules, and where it is going to bind. So the thing is, it has been found that for aptamer, it is not a specific area or domain is binding. Rather than it might be binding like 2 3 factors simultaneously. Maybe some part of the surface glucose protein, and then which is linked to the lipid, some of the special lipid and something. So it's a complex way of recognizing your specific cells. And the way we initially, like our proof of concept data we are trying to establish is using the ellipsometry. Ellipsometry is a very nice method which basically we have used for the fact that we want to see, like, if we make some sensors on the sensor board, we just would like to see here like 10 to 20 nanometer on the surface of that particular sensor. And then, like, there are many reasons. I'm not going through all of this, but the main idea is, like, we were interested about ellipsometry because if we are going to put some sensor into the bloodstream of like vein or something, then there are many cells are passing through. And now if you have anything which has been, your light has been chopped or something, then you might get intensity fluctuations. But if you are measuring the polarization part, so it's give you like the asymmetric values. So even if a red blood cell is passing and your light has been chopped, it will not reflect to the change in the polarization. And also it is not looking at the bulk molecule. So you are kind of developing a sensor when I'm not looking at the bulk part of the whole blood, what is passing through, rather than I'm just looking at the surface, what is happening on your sensor surface. If there is any change between, let's say, less than 10 nanometer range, where you have immobilized your aptamers, you can easily recognize them. And so we have in parallel developed the optical and the electrochemical sensors. The idea is to capture, like we have immobilized things. The idea is to capture those cells at 37 degree when what is our body temperature, and we have to do all the characterization. And so far, what we have found that when we try to optimize the angle of incidence of light and wavelength, and then we faced a huge problem with the angle of incidence, because in ellipsometric experiments, the refractance has a huge contribution to the ellipsometric measurements. So, and then we have tried to optimize like which angle of incidence actually help us to get the best data possible, which was nearby here somewhere. And then we thought, okay, I'll come back to that point later, that which angle we have used to detect this one. And then we have started detecting this one. This is one such electrochemical determination where we have detected like 10 cells per ml. Like normally 1 ml cells of 1 ml of blood contains 10 to the power 9 cells. So our target cells was 10, maybe 0 to 10 cells we can count to these sensors. And also, as we have an idea that okay, this sensor will be kept inside the brain for a prolonged time. So with respect to time, we have to see the change, what is happening in the sensor board, and we have found that with respect to time, there is a change in the impedance as well. And here is the point, like we had to design a special kind of qubits. Yeah, we had to design one special kind of qubit where angle of incidence was really important. And this is kind of a 64-degree angle where we got the maximum signal out of it, where there is no non-specific consequence. This is the big instrument I'm not explaining, but this is the special qubit we had to prepare to get those kind of data. And the idea is like you have a mixture of cells. This is our proof of concept data where we have shown that you have a mixture of cells. Only the target cells has been bound. Rest of the cells will be going out, and the flow rate and everything has been optimized with respect to the blood flow. When you have off target, there is no change in the delta and psi. But when you have the target cells, there is a strict pattern change in pattern of delta and psi. Like the polarization is changing. But I'm pretty sure no one is going to believe like, okay, this is your specific cells that you have isolated from let's say, for example, one cell out of 10 to the 9 cells. So then we have do a very smart trick here, like before, and also like we had a plan to recover these cells out of this sensor board. So what we did basically, before adding these target cells, yeah, it's just the wrap up. It's just the wrap up slide. So before adding the target cells, we have measured how many cells are live, because after the recognition, I have to get back recover these cells. So I have made this surface in such a way that if you change the temperature from 37 to 25 degrees centigrade, the polymer will be swell up and your cells will be flipped. And then we have measured that how much cells are alive. And we have found that we have started with 95% cells. We have recovered 94.60% cells, and you can easily use those one for further diagnosis to confirm it. And then this is the actual board sensor board image, where you can see the cells are captured everywhere. And this is a laser scanning confocal microscopy, where if you change the temperature, you can see from 37 to 30 to 25, there is a release of the cells. I don't know what has happened in the junction of this like bed. Like when there is a change of temperature, some cells are stick, maybe died for some reason. But this is what we got so far. So the idea is you have to capture your cells, then you in situ detect, and then send those cells for further detections. Thank you.